Okay, guys, we're going to talk about geometric sequences. You are going to have this copy, which you're going to put in your journal. We are going to go through and discuss in more detail some other examples and where these things come from, but this is your reference sheet that you're going to have in your journal. So put that to the side for now. You're welcome to take notes on what I'm covering today. You'll notice it's in a presentation format, so I'm not printing it for you because it is pages and pages and pages. However, it is available on the website. So if you need to print out one, you can print it from the website. If you don't have a printer, you can come and ask me to print one for you. And we will do our best to get that figured out. But I can't print them for everybody because it would just be like 5 billion trees we're hurting. So when we talk about geometric sequences, you can write down notes by hand, you can watch intently and write notes later. But a geometric sequence is basically just a pattern over time, right? It's patterns. And you guys have been seeing patterns for ages. But it's a pattern usually over time. So, for example, if we're looking at how high a bungee jumper goes, right? Because when you bungee jump, you drop and then you bounce and drop again, and then you bounce and drop again. But you don't bounce as high. It's not a consistent bounce height because each time you're slowing down, you have less momentum, like you've learned in science this year. So, bungee jumper falls first, goes this far down, then bounces and goes like this. The next bounce, they might go like this. The next bounce, they go like this, right? It is changing over time and it's not linear. Even though it looks like you could draw a line, it's not changing by a linear amount, it's changing by a ratio. So the height of the bounces shown in the table form the geometric sequence. And what I'm talking about here is that 280 and 32 form the geometric sequence. The ratio of successive terms is the same number r. That's called a common ratio. So when we talk about geometric sequences, there's two things you care about. Number one, is it a geometric sequence? I'm going to show you how to figure that out soon. And if it is, what is the common ratio? Because that will help you find the next terms or subsequent terms, which is sometimes what they're called. So in general, geometric sequence, pattern over time. And let's look at some more examples. Okay, so usually the way that this question shows up on a STAR exam will say something about find the next three terms in the geometric sequence, or it might say find the next three terms in this sequence, and you have to figure out if it's arithmetic or geometric. An arithmetic sequence is a type of sequence you've been seeing for years. This is, okay, they add 4 over and over. So just to clarify here, I'll put off to the side. Arithmetic sequence means they add or subtract the same amount. So this is like 2, 4, 6, 8, 10, dot, 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 find the next ones. Oh, they're adding 2 each time. Great. And then when we talk about another type of arithmetic sequence, this might be, okay, well, they have the number 20. What's happening each time? They're subtracting 5 each time. So as you go down each time, they're subtracting 5. So again, this is also arithmetic, right? This is adding or subtracting the same amount each time. And they might ask you to find the next three terms in that sequence. So you just look at what's happened, and then you either keep adding 2 to find the terms, or you keep subtracting 5 to find the terms, and that's good to go. Geometric sequences are not adding and subtracting. Geometric sequences are multiplied by a certain factor, and that's your common ratio. So in order to figure out what that ratio is, you have to go in and divide and see what's happening in each of them. So if you see a sequence that looks like this, you're like, wait, that's not adding 3 each time, right? There's something else going on. Well, take a breath and go through and do the second term, right, divided by the first term. And that's going to give you your ratio. Let's check to make sure that ratio is consistent the whole way through. In order to do that, okay, well now I need to look at my next term, 16. Take 16, divide it by the previous term, which was 4. Did I get the same number? Yes, I have a ratio of 4. Let's keep going and see if that holds true. All right, my next term is 64. I'm just double checking to make sure it's actually a geometric sequence. I do 64, I divide it by the previous term, which was 16, and it's still 4. So my common ratio is 4. The value of R is 4. So to find the next terms, all I need to do is keep multiplying by 4, because this is 1 times 4 is 4. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is, that's where we come down here, 256. 256 times 4 is 1024. 1024 times 4 is 4096. So first you have to find your common ratio. You find that by dividing. This divided by this tells you what that ratio is. Make sure it's a consistent ratio all the way across. If it's a sequence, it should be consistent. Otherwise, it's not a sequence, right? Then you're going to multiply the last number, term 4, so the same one here, term 4, by your R value. And I just marked those two. So since we're color coding everything, I got 4 each time. So then I'm going to multiply by 4 each time. And that's going to give me the next numbers in the sequence. So let's look at this next one. Find the next terms in the geometric sequence. So they give us a sequence. If you look at this sequence, you can see it's not adding or subtracting the same thing each time. Something else is going on there. So we're going to find out what our R value is. So let's start with our second number, 3. And let's divide it by the number that's before it, which is -9. Now, I'm just going to simplify because that's a fraction, and I can see that that is -1/3. Okay? You can put it in a calculator. That's totally fine. Let's look at the next one. So my next one, it has 1, but actually they've made a mistake here because that should have been -1. So just mark that real quick. This was -1. Right? So I'm going to take my next one. -1 divided by the previous term, which was 3, still -1/3, right? I still have my same value. Sorry, my notes got messed up here. My value is still -1/3. I end up smearing this all over the place, but I'm trying. Okay. All right, let's look at the next term. So my next term is 1/3. 1/3 divided by -1. So all I did was put this 1/3 here. And in order to do it by hand, right, I did this -3/3 because that's the same thing as -1. You could have just left -1 there. Either one is fine. But you'll see you're still coming out with -1/3. So our value is still -1/3. And let's check one more just to be safe. And I'm kind of out of colors, so we'll go back to green again. Let's do our -1/9 divided by the term that came before it, the 1/3. And you will see, if you plug that in your calculator or do it by hand, if you remember how to divide a fraction by a fraction, that your number is still -1/3. So our R value is -1/3. All right, I found a consistent value all the way across. Again, you don't have to have every single word written down. I'm doing this so that I can show you some different examples. So to find the next 3 terms, let's see if I can do that. I'm just going to multiply this last term by -1/3 and do that 3 times. So -1/9 times -1/3 gives me +127. 127 times -1/3 gives me -101/81. Again, all I'm doing is multiplying by my R value each time to find the successive term or the next term. That's all that means. So the next 3 terms are 127, -1/81, and 1/243. So Helpful hint. When the terms in a geometric sequence alternate between positive and negative, like you see here, right, the R value has to be negative. So just something to keep in mind. If it's alternating between positive and negative, the R value must be negative. Let's try one more. I'll cover this up so I'm not distracting you. Other one. So find the next three terms in the geometric sequence. 5, negative 10, 20, negative 40. Well, already you know your R value must be negative. That's right, because it's alternating between positive and negative. But let's see what that R value is. Well, what happened from 5 to negative 10? Well, I'm going to take negative 10. I don't remember which color order I used before. I'm going to take negative 10 and divide it by the previous term of 5. And it gives me negative 2. I'm pretty sure this is my R value, but let's just double check and keep going. So then I'm going to take my next term, which is 20, and I'm going to divide it by the previous term, negative 10. And again, 20 divided by negative 10 gave me negative 2. And we're going to check the last one just for good measure. I have negative 40, right? And I divide it by the previous term, which is 20. And I still get negative 2. So the value of R is negative 2. My ratio is negative 2. So to find the next three terms, we're just going to multiply by negative 2. So negative 40 times negative 2 gives me positive 80. Right? All I did was multiply by my R value. Positive 80 times negative 2 gives me negative 160. Negative 160 times negative 2 gives me positive 320. So the next three terms are 80, negative 160, and 320. So this is geometric sequences. When you're given the specific numbers and they just want to know the next three numbers or the next number or the next 5 numbers, this is how you would find it. Sometimes they're going to ask you to find the nth term. And here's what that means. All right? If you have to find a specific term, the nth term means you don't know which one you're looking for. So this is more like when they say, find the 34th term in this sequence, right? You're looking for a number that is way further down the line. And I guess, yeah, you could do it 34 times and figure out what it is, but there is an easier way to do it. Usually, the variable a is used when they're talking about sequences. And in a sequence, each number has a position. So your first number in the sequence, which in this case, the term was 3, is called a sub 1. That little 1 down to the bottom is said a sub 1. The second term in a sequence, so its position is position number 2, the actual term is 6, that's called a sub 2. All right, so this is just teaching you some notation. So the first term is 3, common ratio of R is 2. You can use the first term 3 and the common ratio of 2 to find a rule for finding a sub n. So let's look at how we can find that rule. Okay, you know I like my tables, so we're going to draw a table. If the first term is 3, and we call that a sub 1, and the second term is 3 times 2 to the power of 1, right? That gave us 6. So our second term was 6. That's where this came from. Then a to the 1 times, a sub 1 times R to the power of 1, right? We only did our ratio once. When I look at the third term, my third term was 12, right? Third term, 12. What I actually did there was 2 to the power of 2. My ratio was 2, but I've now done it twice. So this is where you get into a sub 1 times R squared. And you'll notice the pattern keeps going. For the fourth term, 24, it's a sub 1 times R cubed. For the nth term, it would be a sub 1 times R to the n minus 1 power. This is where this little reference sheet that I gave you will come in handy. But basically, you're looking at, this was the fourth term and we cubed it. This was the third term, we squared it. This was the second term, we did it to the first power. The first term wasn't affected at all. That's why there's nothing there. So for the nth term, we're going to raise it to the nth power minus 1. Okay? So you get this formula, which is what's on the formula sheet I've told you can put into your binder. So let's look at some examples of how to use this. These questions will look something like this. The first term in a geometric sequence is 500 and the common ratio is 0.2. What is the seventh term? Yes, you could do that in your calculator and figure it out, and that's fine, but there is a faster way to do it if you use the formula. So write your formula down. Well, if I want a sub n, in this case, a sub 7, it equals your first number times your ratio raised to the power of n minus 1, all right? Well, your n comes from here. It's the same number. So your 7 still stays a 7, but you want 7 minus 1. So you have 500 times your factor of 0.2, which is what they gave you here. So the 500 came from here. That's your starting point, all right? Your common ratio is 0.2. Put that right in there. And then they want to know the seventh term. So a sub 7, and that gives you 7 minus 1. Sorry, I didn't mean to get over that. So now let's simplify. Well, 7 minus 1 is 6. That's where the 6 comes from. So now it's 500 times 0.2 to the 6th power. We teach this here because it looks very similar to the way exponential functions are set up. The seventh term, when you put this in the calculator, would come out to be 0.032 or 32 thousandths. Let's look at example 2. For a geometric sequence, it's telling you a sub 1 equals 5 and r equals 2. Find the sixth term of the sequence. All right, so I'm going to try and use the same colors. They didn't tell us, let's say, they said A1. A1 is 5. Well, that means my starting point is 5. All right, I can put that in. They tell you that the R value is 2. So my R value is 2. And they're looking for the sixth term, which means I'm looking for A sub 6. And it means I'm going to start with 6 and then subtract 1, which means it's 5 times 2 raised to the power of 6 minus 1, which is 5. And 5 times 2 raised to the power of 5 is 160. If you choose to do this by hand, be very careful with order of operations. And remember, your exponents happen before you multiply, right? So really, this is 2 to the power of 5, and then multiplied by 5. That's how you get your 160. The sixth term in the sequence is 160. For these, you really just need some practice. So let's go ahead and practice and see what we get.